So we are back. We are back. Going on with what's been going on with me, anyways. I don't know how often I'll be posting these, but I guess every 2 or so weeks is fine. Or maybe 3. I don't know. Anywho, so our main topic for today is quantum dots, because that's actually what I'm doing a lot of my research on. I mean, sure, right now I'm really in classes, and that's like the majority of my focus, so I don't really have time to be doing a lot of research, which I'm not gonna lie, I kind of hate, but it is just part of life. Anywho, so quantum dots. There's a lot of videos out there about quantum dots and what makes them emit, what types of them there are, and there are plenty, litany of papers on it. In fact, I'm pretty sure this past year or like 2 years ago, someone won the Nobel Prize in Chemistry in quantum dots. So it is a very big topic out there. And although a lot of you may not know what they are, it's entirely possible that you've interacted with them multiple times. One of the big examples of this is like QD-LCD. Please, someone fact check me on this in the comments, but the QD part stands for quantum dots, so they're already in displays and TVs. Some of them, I'm pretty sure, can be in phones and monitors. So it's entirely possible that what you're watching this on has quantum dots in them. So what are quantum dots? So quantum dots are small dots. Quantum is a size. And dots are, dots. Small dots in the range of about 2 to 10 nanometers in size and have about 100 to 100,000 atoms. Specifically, the ones that I focus on are like semiconductor quantum dots. So, for a quick refresher, a semiconductor is part conductor and part not conductor, so semiconductor. So what does that mean? I can probably go deep dive into this in another video, but there are some things that are insulators, conductors, and semiconductors. Insulators don't really conduct much, but like there are thermal insulators and electrical insulators and stuff. As in like, they don't give heat or take heat quickly. So air is a bad conductor because like, think about it in an oven. Right? You can have your oven turned up to like 400 degrees, but you stick your hand in there and your hand doesn't just evaporate. You know what I mean? Exaggeration here. But the metal inside, if you touch it, it will burn you. The metal is a better conductor of heat than the air is, because technically speaking, right? And reality speaking, as far as I'm aware, the metal in there is 400 degrees and the air in there is 400 degrees. But the metal is a better conductor, so you feel it better, right? You feel it more. And then there are things in the middle. For those things in the middle, I didn't include this in the video because I completely forgot about it, even though this entire video is about semiconductors. Quantum. For an example of something in the middle, we'll get like silicon. So silicon at room temp naturally doesn't really conduct the electricity, right? So that is a semiconductor. The band gap is a little bit smaller. So what we can do with that is if we heat it up, we can then have the electrons jump to the conduction band, and then that can conduct electricity. So if you take pure silicon and you heat it up, then that can conduct electricity, right? But you can try and do the same thing with insulators, right? Just give the electrons a little bit more energy and then try and conduct the electricity by making it jump that massive gap. The problem there is you'll probably just destroy the material before you can get it to conduct electricity. Great example of this is like glass. If you tried to heat it up to conduct the electricity, it would just be too hot before it can conduct. So the glass will melt and warp and just break before it will actually conduct the electricity. Silicon is at that intermediate where you can heat it up and you won't destroy the material before it conducts. All right. So semiconductors, that's what I was talking about. Okay. So semiconductors are, as I mentioned before, an in-between between a metal, which is just plain a conductor, and an insulator, which doesn't conduct much. And with the heat example, it's good, but What we focus on is more like electrical conductivity. So as you probably see, if I put this up, this image is from just semiconductor Wikipedia. You can scroll there and you'll be able to find it, and plenty of references there. I should have a link to this down in the description below. Anywho, so a metal has their conduction band and their valence band pretty much interlapped. So at like room temperature, there's such an overlap that the electrons are just in the conduction band overall, and then it becomes a really good conductor because you can just put electricity in there and they all just flow in the conduction band. Wonderful, cool, great. An insulator has a massive gap, and because of just how quantum stuff is. I get that from a YouTuber I normally watch. If I say that a lot, please go watch Angela Clear. I think I'm saying that right. Again, her account will probably be in the description below. Really good YouTuber. A great inspiration for me. But so in that you have insulator. An insulator has a pretty big gap between the valence band and the conduction band. So for stuff to conduct electrically, please, if anybody knows better, you can correct me in the comments. Anywho, so an insulator has a pretty big gap between the valence band and the conduction band, and that means it needs a lot of energy to jump from the valence band to the conduction band. You have to put in a lot of energy, and the thing is, in this gap in between, if you can see my face, is that you can't go in between. Right, there are some stuff you can do, etc. But like in this situation, let's just say you can't go in between. So you need the exact amount of energy to jump this entire gap for you to go through. That's a complete insulator. And a semiconductor is kind of in between. And there are different types of these. So the quantum dots that I'm focused on are semiconductor quantum dots, where we do have a gap. It's not massive, but it's not like super tiny either, right? Where they're probably overlapped. It's just a little bit of a gap right here. And this gap has the same amount of, and we can tune it. This gap is tunable, which is one of the things, which is one of the reasons why quantum dots are so amazing. You have the tunable gap, and this tunable gap is based on the size of the quantum dot. So what we can then do is make quantum dots with this gap have the same amount of energy as visible light. So this means that if you give an electron from the valence band and you give it just enough energy to jump to the conduction band, when it relaxes back, so my thumb right here, when it relaxes back, it emits light, right? And it emits a specific wavelength of light every single time. So this is the tunability that we're talking about. And when we make them bigger, the gap gets smaller and it emits more red light. When we make it smaller, the gap gets bigger and we emit like closer to blue light and everything in between. All of these are super controlled based on the size of the quantum dot. So one of the reasons this is because the color or wavelength of light is linked to its energy. So when we have that band gap, when the electron relaxes or recombines with the hole, right, from the conduction band to the valence band, it releases a very specific amount of energy. And as you can see from this photo here, we have from this formula, we have the energy is equal to the Planck constant times the speed of light in a vacuum over its wavelength. The Planck constant is a constant that's not changing. The speed of light is also not changing. So that means we can directly relate the energy to the wavelength. And since we can control the amount of energy based on the size, then we can control the wavelength. And since that energy is unchanging, the wavelength is unchanging. So we get the same wavelength of light. So this is one of the things that we can do. When the electron jumps to the conduction band, it leaves a hole behind. And what you have is an electron conduction band and then a hole in the valence band. And like, it can like there's a little bit more stuff to it, but what happens is the whole rises away from the nucleus. Is the way I think about it. So the whole rises and the electron sinks to the lowest energy in the conduction band and the highest energy in the valence band. So I've been saying it like they're one thing, but in reality, you have the valence band, right, and it has a bunch of energy levels in between, right? So like imagine this with a bunch of lines in between, and then you have the conduction band, which is even hot. Wait, this was valence, a bunch of gaps in between, and then you have the conduction band with a bunch of energy levels in between. And what you have here is the highest energy level in the valence band is pretty high up there, and the lowest energy level in the conduction band is pretty low up there. And when the electron jumps this band, boom, hypothetically, it emits light. This doesn't happen. The bands are separate. This was meant to be like the electron and the hole that's left behind, recombine, and it emits light. So, one of the things that we can do to get this type of light that we're searching for is confine how far the electron and the hole can be from each other, right? If we confine that, we put it in a space where it doesn't really like, or we put it in a specific area we can control that energy. So we live in a three-dimensional world. There are three ways we can confine this electron hole pair. This is called an exciton, right? Because you excite the electron and exciton. So these things have their own. If you know a little bit about electrons, you know the particle wave duality type thing. And a particle, it has both qualities of a particle and both qualities of a wave. And the same thing happens for the hole, but like the hole isn't a real thing. It's like imagine an empty seat in a oh my gosh, what's that called? In a stadium, like a full stadium has an empty seat, and someone gets up, right? And then as someone else sits down, the seat next to them becomes empty. And then as that person sits down, the next seat becomes empty. And it's kind of like that, that the whole travels, right? There's nothing there, but it's helpful to think of it as if there's something there, right? And those two have their own wave functions together, the electron and the hole, and that is called an exciton. And an exciton is something we call a quasi-particle, because an exciton isn't real, like a real thing, right? But the way these things act together, it acts as if it were a real thing. So it's easier to call them a quasi-particle, which is the exciton that we're talking about. Anywho, so in these quantum dots, what we confine is the exciton, which is the electron hole pair. And there are multiple ways that we can confine this. So you can do a 1D quantum well, 1D confinement, which is called a quantum well, a 2D confinement, which is called a wire, and a 3D confinement, which is called a dot. So how do you confine it? So you have your XYZ plane, right? If you confine it to by one, so it can only go forward and backward, right? Forward, backward, left, and right, but it can't go up and down. That's a well. If you can find it in two places, let me close this one, where you can go forward and back, but it can go left and right or up and down. That's a 2D, so it's like a wire can go completely straight this way and that way. And if you combine it in all 3D, it can't go anywhere, and that's where you get your dot. So we have a quantum dot. There are a bunch of different ways you can confine this quantum dot like this, and there are a bunch of different materials that you can do to confine it. So there are multiple types of quantum dots, right? So there's this core, which is, you can have a core, which is just like your quantum dot, and then you can have a core shell one, which is where you have a quantum dot with something around it to protect it. You can protect it from these things called trap states and a bunch of other stuff. We won't get into it right now, but if you want to, I may include some of these things in the link below. I can do a video about them later. But there are a bunch of different reasons why you can have a bunch of different types of quantum dot depending on what you're trying to go after. So right now we'll focus a little bit more about some of the different types of quantum dot, right? So we already have the core, which is this thing, a core shell, which is just a core with a shell around it, right? Intuitive name. And then there's a couple more types, which is just type 1, type 2, inverse type 1, inverse type 2, and quasi type 2. So this goes off what I was mentioning earlier about the conduction band and the valence band, as well as what the electrons like to do, and what the holes like to do. So the electrons like to sink down, and the hole like to rise up. So like sometimes when you excite it, it's not always like the electron in the highest energy of the valence band that jumps. Sometimes it's a little bit lower, and that jumps to the excited band, right? The conduction band, sorry. And then that means the hole isn't at the highest energy, and it rises up there. What that rising means, imagine the seat in the stadium, is an electron that's slightly higher drops down, right? And that hole goes up to that space that it was occupying. A lot of quotation marks there. And then another electron drops down to this location, so there's now a hole even higher, etc., 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 until you get to the highest energy. And there are like that has some energy like release, and that's usually not in I doubt it's ever in the form of light. There are different ways that that the quantum dot can release energy. One of the things is like phonon coupling, which I don't understand, so we're just gonna gloss right over that one. so I should have an image up here in just a second that can better help you visualize what is happening with like the falling of an electron and the rising of a hole in the different types. So if we look here, we can see the different types. Type 1, inverse type 1, type 2, inverse type 2, and quasi type 2, right? So this image is actually from Core Shell Quantum Dots, a review, classification, materials, application, and theoretical modeling. You'll have that, again, in the description down below, right? So, and that's where you can find this image. If you're in school, you can just log into, I think it's called Science Direct, with your like school account. If you don't have one, trust me, this is where this is from. I'm not stealing their information. But I hope it shows up for everyone. So in this one, in type 1, what you have is the band gap, or between the core is in gray, and the shell is in, what do you call that, beige? Pink? The band gap between those two is very different. So the band gap between the valence band of the core and the conduction band of the core is that gap is smaller than the valence band of the shell and the conduction band of the shell. So what happens here when you create an exciton? Where does the electron go, and where does the hole go? So if you make an exciton here, the highest place that the hole can go, right, is the conduction band of the core. And the lowest place that the electron can go is the highest place that the hole can go is the valence band of the core, and the lowest place that the electron can go is the conduction band of the core, right? So that would mean both the electron and the hole is localized in the core, so the exciton is localized in the core. That's what that does. In an inverse type 1, the situation is flipped. The valence band of the shell is higher than the valence band of the core, and the conduction band of the shell is lower than the conduction band of the core. So let's say you create an exciton here. The hole will rise to the highest place it can go, and the highest place it can go is the valence band of the shell, and the electron will drop to the lowest place it can go, and the lowest place it can go is a conduction band of the shell. So that would mean that your exciton is localized in the shell, which is the inverse of type 1, like we just explained. Now let's move to the type 2 right here. So here, there's a slight difference. right? The it's not so much about the gaps here, but where the energy of each band is, like the valence band versus the conduction band. So here in the type two, the highest place that the hole can go is not in the is not in the shell, but in the core. So the highest place that the hole goes is the valence band of the core, and the lowest place that the electron can go is is the conduction band of the shell. This means that the hole is localized in the core, but the electron is localized in the shell. This means that the exciton is localized in both, but now you have the electron in the shell and the hole in the core, right? Let's move on to the inverse type 2. This is just a situation flipped, right? The electron is localized in the core now, and the hole is localized in the shell. So that's an inverse type 2. And then we get to a quasi type 2. In this situation, right, the energies of the core, the valence band, nope, the conduction band of the core and the conduction band of the shell is almost the same, right? They're like, I will do a deeper dive into these, but this is just a small introduction. And what you end up having right here is the electron isn't really localized directly in the core, and it isn't really localized directly in the shell either. The wave function of it, I should have an image of it here, but I'll save that for another video, right? It's kind of in both, right? And that is a quasi type 2. So those are the different types of quantum dots. I'm sure there are more, and there are even in the same paper. It goes on about like what atoms you would need to make each type. Next time we can go a little bit deeper into the types of materials that you'd use these for. What would you use a type 1 for? What would you use a type 2 for? Or the inverses, what would you use a quasi type 2 for? And in these situations, which atoms would you use? Would you use gallium? Would you use cadmium? Would you use phosphorus? Or, you wouldn't use phosphorus for that. You'll understand when I make the video. But this is just some of the types of quantum dots and some of their properties. What they're good for, what they're not good for, we'll get into that a little bit later. But if you guys have any requests on different videos I should make, please leave them down in the not in the description, in the comment section below. And don't forget to like and subscribe. I feel like I have to say that for YouTube. Hopefully this gets a little bit more popular and more people can see this. But if you have nerdy friends, or if you just want to listen to this in the background, this is what I'm making this for. I have a long drive, so I have these kind of videos playing in the background. If this is something that you guys are interested in while you're cleaning a room or something, please let me know down below what you guys are interested in.